Okay, let's start. A little bit of noise here, but hopefully we'll survive. Are people hot? Should I close it so we don't? I think that's going to last for a while. Okay, just a little bit. Okay, so I posted this on Piazza. I think yesterday or Saturday. Just I don't know how many people caught it, so I wanted to kind of go through it because I did get a few questions. What's going to be on the midterm and kind of where it's going to be, things like that. So hope everyone can see that. Okay, so we're going to do it during normal lab hours on Friday or class hours. So here. Office hours are going to be just during lab hours and my normal office hours after class. So hopefully that's going to be enough. If you guys need more, let us know. We can maybe try to accommodate a few more office hours. People asked about the cheat sheets. So we're going to do one page, both sides, or one sheet, both sides if you want. If you don't want to have any, that's okay as well. Calculators are okay. Hopefully you won't need them. It'll be something that's really simple to calculate because that's not what this whole thing is going to be about. We'll have 5 problems that are kind of short. So 10 minutes each, short and sweet. So the idea is to test you on a bunch of different topics that we covered, and I sort of put together a list here. So bipolar and MOS small signal model generation analysis. So that will be embedded as part of some problems. Just so those are kind of the things that if you read and you go like, I don't know if I understand this concept, well, that's what you should kind of maybe focus on this week. So single and multiple transistor amplifier circuits, both bipolars and MOS. We did cascodes, we did cascades of transistors, active loaded, passively loaded. So all these things kind of are, okay, I think it wants to be loud, are fair play in differential pair amplifiers, kind of the half circuits, for example, things like that. Common mode rejection ratio, input offset voltages, what do they depend on? Maybe a quick reminder from there, an application of either a formula that we did or some similar way of doing it. We talked about biases and current sources. So again, understanding what's the minimum output voltage that the source presents to the load, what's the systematic gain error, where that comes from, different topologies, and knowing how to analyze and go around the KVL loops in these topologies. That connects to sort of the biasing. Again, how do you bias such source? We did the triode device bias and all these other things. Sizing the device larger gives you smaller overdrive, so you can, or sizing the device smaller gives you larger overdrive, so you can get an overdrive multiplier, right? These kinds of concepts. And then sort of lastly, some very basic principles of compensation. We're not gonna, for the midterm, do like a CMOS op-amp compensation. So just starting from some transfer function, maybe how do you go about doing it, or what we did in the homework, that kind of style, like idealized op-amp and something that happens to it, an op-amp that has 2 or 3 poles, what happens, right? So hopefully we're going to shoot for that to not be kind of the extent of homework 7 kind of derivations, but something that just shows the basic understanding of you knowing what the pole movement is or what the dominant pole does to the circuit in terms of stability, things like that. Okay? Just to give you an idea, and take a look at these topics, take a look at the midterm problems that you've figure it out yourselves. Take a look at all the homeworks. If there's anything in the homework solutions that we posted that was not clear or you don't understand, that's probably the likely thing you should really kind of dig a little bit deeper in, because these concepts will show up in problems. Okay, so that was sort of about the midterm. I wanted today to kind of wrap up the high gain amplifiers and then start a little bit on, again, the frequency response of some of these topologies that will then take us into compensation of these particular topologies. So just over the end of the lecture, we sort of sketched the folded cascade, which was one way for us to try to get a high gain amplifier without having to pay the price in very small output swing, or in other words, without having the need for very large power supply in order to fit the headroom of all these cascaded stages, right? Because remember, in telescopic, we had to fit like 2 diode stacks on each side, so to speak, to be able to get the output, right? So in folded, we try to avoid that a little bit, and I'm going to repeat the schematic just so people have it, and we can do the analysis here. So we're going to have the supply, have the current loads or current sources from a bias. We're going to do 2. And here we're going to have okay. And we're going to take the output from here. And now, this is sort of our cascaded structure. So from the output, if we look down, we see a stack. If we look up, we see a stack. Now the question is, where do we fit the input, right? And we said we're going to have this input. Okay, this is VSS. And then we're going to go and connect this input to the source of these transistors. Okay, let's label them just because we're going to use these names later. M1, M2, M3, M4, M5, M6, 7 and 8, 9 and 10. Let's say this is M11. Oops. So we're going to have this one drive V bias. This V bias 2 will set this so that there is a current here, let's say IB1, and then the current that flows to the output stack is going to be the difference of the two, right? So IB1 minus I bias over 2. So in this sense, this IB1 bias, one of the conditions is going to be is greater than I bias over 2. Okay, so in this topology, can anybody tell me what's the polarity of this left input versus the right input? Which one is plus, which one is minus? What's the phase shift from gate to drain? Always. 180 or pi, right? Okay. And from source to drain? Yeah. Same sign, right? So 0. Okay, so that's the only thing you need to analyze this. So you take the input and you go, how do I get from input to the output, right? I have to traverse some gate drain connections and some source drain connections, right? So let's pick this one. I go gate drain, so I'm getting pi. Now I'm over here. Now here I go source drain. Right, so that's a 0. Then this is just the resistor, right? So I'm just developing that voltage on this one. So then I'm driving this guy, right? So from here to here, it's pi. And then again, up here, it's 0, and I'm at the output. So how many pi's do I have along the way? 2. So that input is then V plus, right? And the other one is V in minus. We can check it because it's pi over here. And then once you come here, you get a 0, and you're at the output, right? So when this input increases, the output increases. When this input increases, the output decreases, right? Or in other words, when this input decreases, this input also increases, right? Okay, let's take a look at what the gain is. We said that for the amplifier, multi-stage one, whatever, we always get this relationship, right? This just comes from the fact that I model any amplifier as GM V in and this is V out, right? So my VO is minus GM R out V in. Right. Okay. So in this case, what is GM? Anybody has any ideas? GM just turns input voltage into the current that gets routed through the circuit, right? So if I'm looking at this input, which transconductance first turns the input voltage into any current, right? Into the, yeah. So if I move my input voltage a little bit, this current will change proportional to the GM. And now you're looking at this current going through the rest of the circuit, right? These are supposed to be current sources, right? Because they're just biased. So they're really giving you constant current. So whatever delta I you had here needs to kind of come from this path down, right? So there's minus delta I here. Correspondingly on this branch, if this one has minus delta I, then this branch over here will have plus delta I. So that transconductance that shifted the voltage to current, that current is now going here. And the rest of this circuit is just a current mirror, right? So it will essentially take this delta I and move it to the output. So it's really not doing anything to that current except mirroring it. So therefore, the only thing that really converted voltage to current was this GM1, right? And OK, because we're referring to this input, so it's minus GM1, because my overall polarity is positive, right? People understand this? So this is the useful way of quickly analyzing the amplifier, right? You go by the functionality of what we intended these different pieces to work, right? Remember, when we did folded cascode, I first drew on this piece over here, I first drew just a current mirror. So that's the general functionality. Current mirror will just move whatever changes on the input to the output in current. So it's really not doing transconducting. It's not moving voltage into current or anything like that. So the only piece that moves voltage into current is this input diff pair. Therefore, the whole transconductance of the circuit is based there. OK. So then we need to figure out what is our out. OK. And for that, we can go full blown. So I'll just redraw a little bit of it and then really try to simplify, because I don't want to do the full small signal kind of analysis. So this is what happens from M3 and M4, because gate and drains are grounded. So this is M3, M4. And then as I go down, I get another part of the cascode. These two gates are also grounded. Get first diode connected and a second diode connected one. And now I'll apply here V test and look for I test. And then I have another piece, so the input is OK. So I can take this and move it into a half circuit if I do one approximation. And the approximation is going to be that, remember how last time when we did this elaborate derivation, we said that this piece over here where you have a diode connected device, we did the PSRR and you saw that in the end some were 0, right? After we kind of did a lot of circuit equations. But really, it all boiled down to the fact that if I have a device like this that's diode connected, and constant current is running through it, then its VGS doesn't really change, right? Its VDS also does not change because it's here equal to VGS. So therefore, any change in voltage that goes from here out here is not really going to change anything on the VGS of this device. So I can assume that essentially small signal voltage drop across that device is 0. And since that's a resistor, that means that the small signal current that flows through this is 0. okay? Because that diode is sort of holding its voltage. See what I mean? And because of that, I can essentially assume that this path that is X'd, meaning that these gates here are actually as good as connected to ground. Okay. If you go and kind of derive everything, you'll see that pretty closely you get that. And we've already done it once for this power supply rejection. It was exactly the same deal. So I encourage you to, if you're suspicious, go and do it. But this is where kind of the logic comes from. And so in the book, they kind of also talk a lot about that to do a shortcut. I did it last time because I wanted to have one place where you can see it with your own eyes on the formulas. But really, that's what it boils down to. That as a first rule of thumb, all these diode connections you can treat essentially as a fixed voltage, right? And once that happens, you can collapse this whole structure into just the half circuit that's visible from the output. So you have, this is M8, this is M6, M10. So you're going to have M8. Oh, nice and quiet. And then M8's gate is going to be at 0. And then M10's gate is at 0. So that just leaves R10, RO10. And then at the top, we have M6, and its gate is at 0. We have VT. And then here, instead of M4, because this is grounded, I can immediately turn it into RO4. And then at this connection, I also have whatever's left. M1 and M2, they're just turned into RO2. And ground. Right. OK, so now if you take a look at this structure, you tell me what's the output resistance. We can do it as two halves, like first the R up, R down, and then like R up, right? So let's say what is R down? Inspection, cascode, formulas. OK, yeah, close enough. So that's, I'll just write it as numbers so you know where it's coming from. So GM8 times RO8 times RO10, right? Approximately. There's some other little pieces, but this is the gist of it, right? OK, so what is R up? That's R up, and then we have R down. So we have, I'll just write the whole thing. So we have GM6 times RO6 times the tail, and that's RO2 now in parallel with RO4. So yeah, if RO2 and RO4 are the same, then we're going to half. But on ballpark, it's similar. OK? So then our R out is really R down in parallel with R up. And that's roughly, I'm just talking about the order, is GM RO square. Right? And then you have another GM from the capital GM. So our AD is proportional, again, to GM RO squared, which is the same as we got in the straight telescopic cascode. But as you'll see shortly, we do have some benefits. And that's that we sort of eliminated the total height, the stack, because we eliminated how these two input pairs, so the tail and the input diff pair, eat up into the overall headroom. Right? We sort of had to accommodate that as well on the structure. So with that, we can sort of take a look at the biasing. And so V bias 1 would be obviously V overdrive 1 plus VTH. And we had this condition kind of on I bias versus IB1. So V bias 2. So V bias 2 is over here. You know, if I want to maximize the swing at the output, what should I set my V bias 2 to be? In what exact condition should I keep these two transistors so that I kind of maximize my output swing? What should be the VDS of this M4? It's a current source, right? So how do we set our current sources, the output? What's the minimum a current source needs across drain source to stay in saturation? I'm hearing VTH, something else. What was something else? VOV, okay. Yeah, in some cases we had to keep VTH plus VOV, but that's to kill the systematic gain, right? Error or something like that, or that was how the cascode was structured. Here, it really is just VOV, right? So we're going from VDD down by VTH plus VOV, and then we go up by VTH. So that leaves us with only VOV here. So that's VDD minus VOV, I think it was 4, right? Yeah. Okay, and then because right, so I'm looking at because I want to leave VOV across VDS of M4, I have to, the bias would be at VTH plus VOV, right? So bias 2 is VDD minus VTH minus VOV. Okay. That guarantees me that M4 drain source will be at VOV. So this voltage over here will be VDD minus VOV. Okay. Now from here, I can adjust V bias 3 so that I can get the best swing on VO. Okay, so what would V bias 3 have to be? Take a look here. This voltage is at VDD minus VOV. So again, I have to come down by how much? So this point here is VDD minus VOV, right? By how much do I come down to V bias 3? Yep. So you come down. So we had VDD minus VOV4. And then we also come down by VOV6 plus VTHP. And so if that's the case, then what is V out max? What's the highest voltage that this V out can go? Yeah. You're in the right direction. So can you speak up? What did you say? Plus VTH, right? Yeah. So you're at V bias 3. This guy can climb up, right, by VTH. So if you look at here, you essentially get your V bias 3, but you can get rid of this piece over here. Okay. Okay, so that's VO max. So we're looking at the total swing here. What is VO min? Okay, n plus VSS, right? Okay, so how did you figure that out?
You go up to 2 VGSs from M2 and M9, and then you subtract the VTH going up from gate to drain.
Okay, yeah, great. So the idea is with all the current sources and current mirrors, we do sort of the KVL around VGS voltages, right? So you go from VSS up this VGS, because they're connected. Then you have a bridge to this VGS. So now you know at this gate, you're 2 VTH plus 2 VOV. And then you have to come down by VTH. Right? So that's still keeping M8 in saturation. Right? So VO meaning will be VSS plus we had M9 and M7. Right? So we had VTH N plus VOV9 plus VOV7, and then minus VTHN. So we had another VTH. OK, I'll write it and delete it then. Right? N, and then minus VTHN. Right? So these two are done. OK. So that's VOV min. Notice that I have a little bit of a problem here, right? This VTH. And this is kind of well understood because when you look at what we talked about, cascode, current sources, this was the price, right, for the cascode. Now, what did we use to kind of alleviate this? That was part of sort of the biasing circuit, right? That was on the side of some other cascode topology. Maybe people remember. When we did the first cascode, we exactly got this issue that it's not just overdrives adding up at the output, but also this annoying threshold voltage, right? And so we did something with the cascode to be able to kind of get around that. That's how you did the biasing, right? To be able to do multiple VOVs. Yes, and that then became part of some other topology that we talked about. Begins on S. Such, right? Such cascode. That's where you you have the level shifting device that eats up another VTH. And yeah, we'll do a short example of that, but later. But this is just kind of where things are. Okay, so here can replace the current mirror. For lower VO min. Right. Okay. Just in short, and you know, if we look at the poles of, and we'll address this in a lot more detail later, but if you look at the poles, and this is again kind of a nice thing about cascodes in general, and we mentioned last time, cascode is nicer than two-stage simply because it has one dominant pole, which was this R out, which is pretty big, times the output load. And then another dominant pole, and then another pole was actually pretty far away, and that's because it was related to, in this case, it's GM6 or GM5, because you're looking into the source of that transistor. In the cascode, it was kind of an NMOS that was cascoding over M1 and M2. Here, it's just a PMOS that's cascoding over M1 and M2. Right? So again, it's GM6 times CS6. meaning total capacitance at the source node. Right. In folded cascode, it's actually a little bit, this pole is not as high up as in a normal cascode. And the reason for that is that receiving transistors are M5 and M6. So this interconnect cap is a little bit bigger because you have to go from an NMOS device in layout to the PMOS device. In a normal cascode, these two could be kind of very close together, so just fingered, right? And so you get a little bit lower pole, but it's still much better than two R outs, right? From first stage and second stage, like you would get in a multi-stage configuration, right? So for same gain, you get a little bit easier time dealing with compensation, essentially, and stability. Those are kind of the biggest advantages of this. Okay, so now the question is, this is okay, but I'm not really happy with GMRO squared. I want to go higher. I want to go from here higher in gain, right? The higher gain I have, the better CMRR and PSRR and all these properties, right? So how do you do that? I can, but then that was my problem. I get tinier and tinier kind of output range.
You can do a super fast like the homework. You put a gain stage.
Oh, you mean the feedback thing? So okay, yeah. So that's an idea. So active cascode. So just for review, for everyone to sort of catch up, what we're talking about is something like this. This is your V input. And then here, what you do is instead of just putting the bias voltage, you put an amplifier, and then you feed back. So this is your V bias. So what this does, if VI goes high, this goes low, this guy goes high. So notice what happened to the VGS of this device, right? It got stretched, right? Previously, if there was V bias on this node would not move. And the only change I would get would be from this node going down, right? But this way, I'm actually getting, for one change in VI, I'm getting a bigger change on this guy, right? So it's kind of like, for same voltage change, my transistor has larger GM, right? Because this current is GM times V in, right? So for same voltage, if this total thing is larger, then for same voltage, I got a larger GM. Or for larger voltage, I have the same GM. See what I'm saying? So the net effect of this is that this is M1, this is M2. This feedback boosts my GM2 to effectively be 1 plus A times GM2. Okay. Notice here that if I'm looking at just the overall gain, again, it's minus GM times R out. My GM hasn't really changed, right? Where's the transconductor here? Where does V in become current? In M1, right? And after that, it's just that current going to the output, right? There's no current going here. So any change here in delta I, it goes straight to the output. But what really changes is the R out, right? So this delta I is just GM1 times V in. So this must be my GM. Right? But R out is now affected by this boosted GM2. Now, what would be the R out without the feedback? Okay, yes, but it would be GM2 times RO2 times RO1, right? But now I am adding this 1 plus A factor, because this is my new effective GM with feedback. Okay. And now, of course, since my ADM is a combination, right? Now I get my previous sort of GM RO squared times 1 plus A. Okay. So let's take a look at, okay, I mean, I'm neglecting a little bit of GMB and things like that because that's not really important right now. Just it's important to see where this factor stacks up, right? And how it helps me. And now this A could be another GMRO. If I have a single stage amplifier here, it's likely going to be that its gain is something on the order of GMRO, right? So I'm then getting something like a GMRO cube. Okay. But if I want differential input, I need to turn this into something more complex, right? Because I need sort of another input. So we're going to do now, the time that remains, we're going to do a differential folded active cascode. This is like putting it all together. It's like a big amplifier. So let me draw it. Don't get scared. The whole point is that once we draw it, you see this big thing and you go, oh, I understand it because I understand the pieces, right? I understand what each piece does. Therefore, I understand the whole thing. Okay, again, we have our source. That's the same. And then we're going down. And then here, these are our cascoded devices, right? So what we're going to do is just like we did in the previous one, we're going to take the source, feed it back, and into the gate through some amplification. We'll label this A1. And then this we're going to keep at V bias. In this case, we use like 3. Yeah. Okay. And then here, we're going to do the same thing. Okay. And then we have our bottom part. I'll have to draw it a little bit better. Again, we know that this part is the cascode part. So again, I'm going to take the source and then move it back, minus, and then a plus 4. Okay, so there's going to be, again, on this one, again, feedback. We'll label this, let's say, A0 or A2. Okay, let's make it A2. Consistent. Everything wants to go away except 0. minus goes into feedback, and then V bias 4. This is VSS. M6, M8, M10. And now what I'm going to do is do a trick here that will help me kind of get lower output voltage. So I'm using this guy I'm using this guy sort of to level shift the voltage, so I can only have like VOV over here at the output and not VGS plus VTH plus VOV, right? Those are the current tricks that we did for low headroom current sources. And then since these are the cascoded nodes, I'm going to take my input. And then move one here and another over here. Okay, I hope I got all this right. Yeah. So this is our circuit. Okay. So each of the cascode transistors is now gain boosted. There's another expression for this is gain boosting. And then I take my VO over here. So if we take a look at GM, what is GM in this topology? We're going to label this V in plus and V in minus, so this is non-inverting amplifier, right? What is GM? Don't get scared with all these like feedback things. That does nothing. That just conducts current and shields the output a little bit from the supplies, a little bit more, right? Yeah, it's just little GM of this M1 or M2, right? Again, think about where the voltage gets translated to current, and then think where the current's flowing, right? This delta I cannot go up, so minus delta I is here. This guy just boosts. We've already done it on a simpler example, right? Previous one, where this thing, you know that this thing only affects the output resistance, right? But doesn't really process the current. There's no current going this way, right? So all the delta I has to come down. Same thing here. This is minus delta I. This is delta I, and that delta I has to show up at the output directly. And if I'm testing for if I ground this node and I'm just testing for current, which is a test for GM, I'll exactly get the sum of these two currents, right? And this, again, just mirrors whatever this current is over here. So I get these two. OK? So what is R out? Again, we have kind of R up and R down. So what is R up? Mm-hmm. Which one? OK, and? OK, parallel with RO2, right? Yep. And what's R down? GM8 times RO8 times RO10. Yeah, that's it. And now, since your A is, we can sort of draw quickly what A1 and A. So A1 could be something very simple like this. Right? And A2 be something that looks like this. Just an inverted version. And why one versus another? What was going to determine which of these two I use as A1 or A2? If I'm pulling the output from here or from here, what's the polarity of these two? What's the polarity of this one? Sorry, this one over here. It's a plus, actually, because it's a pi over here and a pi over here, right? And then this guy is minus. So same here. This guy is a plus. This guy is a minus. So one of these has to connect to what? Take a look at the previous. One connection is the source. Another connection is this, right? These two better be very close, otherwise you're completely saturating. This is not small signal, right? So assume this is a reasonable gain. V bias has to actually be very close to this voltage, right? So then V bias has to be very closely related to, you know, VOV plus VTH and that kind of business, right? And one is lower, another one is pretty high, which means that if you go back to this, one of these ports is really, let's say, in our case, V plus was really high or really low, right? So if V plus is really high, then you want this topology over here, because in this case,